Okay, can you hear me?
Yes.
Great. Um, well, welcome everyone. We'll go ahead and get started. Um, I'm Taylor Johnson, and I'm as the VNN account. And for some reason, it looks like my video may not be showing. But I'm at Vanderbilt, and the other organizer of this workshop is Cheng Lu, who I'll let introduce herself.
Yeah, thanks. Hello, everyone. I'm Chang Liu. I'm an assistant professor in the Robotics Institute at Carnegie Mellon University.
Great, thanks. So we'll start to get going. So we tried something different with this based on the original sort of guidance we got from the other CAB organizers, which was to try a flipped classroom. I'm not sure if any of the other workshops decided to give that a try, but hopefully you've viewed some of the videos that we shared before the workshop. But if not, the speakers are going to give a short introduction to their work as well, just to put things into context. All right, so this is the third iteration of VNN. So last year it was held with a AAAI Spring Symposium, and before that is an informal gathering as far as we understood. And this year we added in the first iteration of a competition on neural network verification that was managed through GitHub. And you can find more details at this GitHub link. And we're going to, at the end of our program, talk a little bit more about that. So this is an overview of our program for today. As mentioned, it's in this flipped classroom format. But the speakers will give a brief short introduction up to a few minutes for the invited keynote speakers who we'll introduce in just a minute, and for 1 to 2 minutes for the paper speakers. Following that, we'll talk about the results of the verification of neural network competition, and then talk about future plans and discuss how that went and other suggestions that that you might have for how the flipped classroom approach went. So our first speaker then, and we're a little bit ahead. We didn't have that much introduction. I guess let me just mention the logistics to start with. In terms of Q&A, so you can post questions in the Zoom chat, in the YouTube live comments, or on the Slack workshop. We'll try to monitor all of them. If we miss anything, we'll apologize in advance, but we'll try to get to everything. Everyone is muted. It should be configured so that you can't unmute yourself unless you're one of the presenters. But if you would like to verbally ask your question instead of posting a message, feel free to raise your hand or type a comment and we can unmute you. Otherwise, what we'll do is Cheng Lu and I will read the questions that we get aloud if you don't want to ask them yourself verbally. All right. So I'll go ahead and introduce our first speaker, then Cheng Lu will introduce our speaker after that. And then we're going to kind of go alternatingly with the different speakers. So it's my pleasure to introduce Professor Pavithra Prabhakar, who's an associate professor at Kansas State University, and has done a lot of very interesting work in verification of cyber-physical systems, and has some recent work on applying and developing verification methods in the context of neural network and AI-controlled cyber-physical systems. Part of her overview talk that hopefully you've watched, but that I presume she'll, give us the short couple-minute introduction to, is based on a NeurUps paper that they had last year with an interesting way of abstracting neural networks. Professor Prabhakar's won a variety of awards, such as the NSF Career Award and an ONR Young Investigator Award. So with that, I can go ahead and hand it over to Professor Prabhakar. Let me stop sharing.
All right. Should we be able to hear me?
Yes, we can hear you. And I see your slides. So.
All right. So thanks for the introduction. So I'll just summarize the main points of the talk, and hopefully will not take a long time. So the context for the work is AI-controlled cyber-physical systems with autonomous vehicles that operate in dynamic and uncertain environments. Traditional controllers are now being replaced by learning-based components like artificial neural networks. And the main research problem that we are addressing is how to ensure correctness of these AI-controlled cyber-physical systems with respect to properties like safety. And in order to understand the execution of these systems, we can think of as having two blocks, one corresponding to the dynamics of the physical system, and the other corresponding to the controller, which is, in this case, a neural network. And in order to analyze safety, we need to compute the reach set, which is the set of all states that can be reached by the executions of the system. And that can be done by iterating over two primitive computations, one which is computing the one-step post set of the dynamical system, and the other which is computing, given a set of states that are sensed by the controller, what are the inputs it is generating. And once we have these two operations, we can iterate over them until a fixed point is reached. So there are a lot of issues, which I'll not discuss here, but I will focus on computing this output range for the controller, which is one of the crucial primitives that we require. So essentially, we have a neural network, and we're given a set of initial valuations for the input nodes. And we want to compute all the possible output values for this output node that are generated by these initial values. And one of the popular existing methods is based on constraint solving approaches, wherein you encode the input-output relation as a set of constraints, which we're going to denote here by this encoding of XS. So it's a set of constraints whose variables capture the values of the nodes at all of these different nodes in the neural network. Once you have this constraint, then you can optimize and find the max and min values at this output node subject to these constraints, and that sort of gives you the output range. Here we are just focusing on the output range, but it could be any output set because we have just one output variable. All right, so the problems with this constraint solving based approach is that the size of the constraints grows proportionally with the number of nodes or the neurons in the network. And the constraint solving problem itself is a computationally hard problem. It's an NP-complete problem. And so the growing size of the constraints is going to be a bottleneck towards scalable analysis. And there's a lot of effort on trying to find efficient algorithms to solve these constraints, as well as find subclasses of constraints. However, what we talked about in the talk is an alternate approach to essentially construct a smaller neural network which can capture the input-output behavior, but since it is smaller, it will result in smaller constraints. that need to be solved for. Or alternately, one could use an alternate approach to analyzing neural networks, for which also you'll have a smaller network to analyze through this abstraction procedure. So essentially, given a large network, we are going to abstract it into a small network. And what we want to guarantee through this abstraction is that the input-output relation of this neural network is captured by it. If we expect an exact input-output relation for this smaller network, then there is very little reduction that is typically possible. And so what we look at is a new data structure called interval neural networks, where we basically allow interval weights on the edges and biases. And that leads to a non-deterministic system, which can now capture multiple output values for a given input value. And that way it can over-approximate all the input-output behaviors of this network. And once we have this interval neural network, which, the size of the interval neural network can be controlled by either merging a lot of nodes or merging fewer nodes. But once we have the smaller network, we can then use some simple changes to existing encoding mechanisms like MILP encoding to check for safety analysis. So basically, in the talk, we get into more details about what this abstraction has to be so that it guarantees this over-approximation, and how do we change some of the existing techniques, in particular this MILP encoding, to address this interval neural networks, which now don't have unique weights on edges, but interval edges. And here is one of the results from the experimental analysis. So as we look at more and more abstract nodes, that is, you divide the nodes in each layer into fewer and fewer groups, the time to do the analysis increases because the nodes are increasing. But on the other hand, the precision of the output range also increases. That is, you become more and more precise as you look at larger and larger number of abstract nodes. And what we observed was that even for a particular number of abstract nodes, the time to solve the constraints might vary drastically because of the way the partitions are created. And so there is further need to do more analysis on what kind of partitions will lead to good abstractions that will be helpful towards successful verification. Okay, so with this brief introduction, I think I will stop and take questions.
Perfect, thank you. So there are a few questions coming in kind of across our platforms. So there's, I think, one from Stan in the Slack. Do you want to just ask your question verbally, Stan?
Sure. So it was in reference to, there was a talk this morning in CAV on the neural network session. I'm not sure if you had a chance to see it, but it was, it seemed like the abstraction that they were computing was very similar to the interval neural network, except they had some sort of concrete goal in mind, like they wanted to see what the maximum of one of the outputs of the neural network was, instead of what's the set of possible outputs. And so then the advantage of that, it seems like, is when after they do the abstraction, they don't get an interval neural network. They just have a sort of a basic neural network that's guaranteed to compute a higher value than what the original network had computed. And then they can use off-the-shelf tools. And I don't know if you had a chance to see that talk, and if you had other comments on the comparison between the approach you proposed here and the approach that they were using.
Sorry, I didn't get a chance to look at the talk. Yes, in the context of, I mean, as you already know, probably, in the context of AI-controlled CPS, we want to compute the output range because that is basically what is the input to the dynamics. But I mean, in terms of answering whether one could compute a max using this approach, it's not clear to me at this point. but there might be some way to alter the abstraction procedure to achieve that.
Okay, thanks.
Okay. There's a couple in the YouTube live stream that we'll get to in a moment. But there's a question in the chat from Philip. In the main presentation, your constraints could also be formulated as an SDP. He thinks, have you tried that alternative?
I haven't tried. So the so the challenge would be, I mean, the purpose of doing the MILP encoding in the first place here was to show as a proof of concept that we could consider these different approaches that exist for neural network to also interval neural network. But as I mentioned, an alternate technique for analyzing neural network that can be extended to interval neural network could very well be applied here as well. So the main thing we wanted to demonstrate was that there is some merit in trying to do the abstraction into the smaller neural network, which will reduce the complexity of any analysis method that we would use. And that could be either MILP or SDP or any other abstraction-based approach, an SMT solver like ReLUplex and so on. So yeah.
All right, thank you. The first question from the YouTube live stream, thanks for the talk. You mentioned CGAR, I think referring to a particular slide in the full talk. If the overapproximation is conservative, it may take a long time to converge to a result. How could we cope with that issue in practice?
Yeah, so I think that's a good question. So in general, we will need to look at heuristics for what heuristics will enable converging faster. And the counterexample guided analysis is going to be based on a safety analysis we're doing. There's going to be a safety property, which will hopefully guide the refinement in a direction that will enable the analysis of these safety property quicker. But in terms of heuristics, there is a lot to be done. So some of the things we are looking at are trying to investigate some kind of a notion of approximate bisimulation, which might tell us which nodes are closer in behavior and try to merge those nodes. So I don't have a definitive answer for what might work, but there are some heuristics that we are considering at this point.
Okay, thank you. Another question from the YouTube live stream from Bart Hoxa. Are there bounds on the overapproximation?
Oh, so there are no quantitative bounds on the overapproximation, and this is sort of typical of most abstractions. And that is precisely the reason why we have methods like CGAR, is to reduce the amount of overapproximation, not in a very quantitative sense. But there might be other approaches that we are currently investigating, which might be able to give such a bound on how far the overapproximation is in terms from the actual output. And so, yeah. So so there is no bound as such for the abstraction that we consider at this point.
Okay, thank you. Let's see. So there were earlier a couple questions in the Slack, some that Chenglu and I prepared, but also I think, let's see. I think he's on. Pranav, we'll get to your questions now. Do you want to ask them verbally, or do you want me to just read them? Okay, I'll read them. So there were two questions. The first one was ACAS-XU is a relatively small network, which is one you had, I think, done some evaluation on. Have you tried abstracting larger networks, both in terms of the layer width as well as the layer depth, so number of layers?
Yeah, so we haven't looked at larger networks, and certainly we will look at it. The main reason for our experimental evaluation was to investigate the trade-off between the time for analyzing the smaller network versus the precision of the output. And I think our experimental results sort of try to highlight that trade-off. And the MILP-based encoding is one particular approach, and it has its own limitations. And I guess Sriram has a tool called Sherlock, which does a much more sophisticated encoding of the neural network, and that will be able to illustrate some of the trade-offs with what happens when you look at really large networks. So the main comparison that we wanted to do was what happens when we do the abstraction in terms of how much precision is being lost versus how much more time is being added to the analysis time. So we will be doing analysis on much larger networks, but we ran into some bottleneck with even the ACAS-XU or smaller networks when we put it in the closed loop with a dynamical system, because encoding-based approaches don't scale that well, especially the MILP-based encoding with that big M methodology that I discussed in the talk, where the value of that M keeps increasing with the number of iterations of the bounded model checking that you want to do with the closed loop system. So those are some things we are tackling, and yeah, it would certainly be interesting to stress test our method with much larger neural networks.
All right, great, thank you. So I think that covered the second part of that question. Then the second question from Pranav was, are there situations where some ACAS-XU properties become unverifiable because of the abstraction, so sort of on the coarseness? So I think a few questions have tried to get a sense of that.
Yeah, I think we didn't do an exhaustive experimentation with the unsafe set, which we are currently doing for the cigar algorithm. But in this context, we were just focusing on output range analysis. So we didn't really look at different safety properties, but the output range that I showed in that in the slide, let me see, I think it's the next slide. Sorry. Okay, so the output range that you see for when we look at very few neurons as abstract nodes is pretty high. And so if there is any reasonable safety constraint that is close to the output, it will, of course, not prove safety of that particular safety constraint.
Okay, I think another question on the Slack. Would you like to ask it verbally or just read it? I'll just read it. how does the interval neural network plus MILP encoding compare to abstraction-based verification in certain abstract domains, such as intervals, zonotopes, or polytopes, which are being used in some of the other approaches for neural network verification?
Yeah, I mean, that is a very interesting question. So the abstraction-based approach is orthogonal to the abstract interpretation kind of methods because, I mean, this is just doing a reduction of the network, and one could use even methods based on symbolic execution to do the reachability analysis on the interval neural network, if only we can handle those intervals on the edges rather than just the just unique points. And that is also something that we would like to explore. But essentially what I'm saying is that this MILP encoding can now be replaced also with an abstract interpretation-based approach. So our method can be used in conjunction with such an approach as well.
Okay, great. Thank you. So looking at the schedule, we have about one, maybe 2 more minutes left. We can, if there's any others from the audience, please let us know. Otherwise, while we wait for maybe one last one from the audience, we can go to one of the ones that we had prepared after watching the talks. And you've talked a little bit about it. It kind of comes back to one of the earlier questions in your response to one of Pranav's questions. So you were discussing a bit about what you're doing in the closed loop case. It sounded like with ACAS-XU. Could you talk a little bit more about what you're doing in the closed loop case, please?
Sure. So what we tried to do was look at, let's say, a discrete time linear system as a dynamical system. And you can then encode the input-output relation of that dynamical system, this part, also as, essentially you can even write it as a linear constraint. So the closed loop is going to be a mixed integer linear program. But let me see, in the encoding that we looked at, I think this one, we needed the value of this M, which was an upper bound on the values that any of the nodes in the network could take. And what would happen in that particular closed loop system, as we looked at longer and longer unravelings of the closed loop, the value of M could become too large and not efficient for the MILP solver to handle. So we are looking at methods to encode where we can somehow contain the size of this M that we need to use when we look at longer and longer bounds on the unrolling of the closed loop.
Okay, great. Thank you. Yeah, we look forward to seeing that and hopefully in the future being able to talk in person about such things. So we're about out of time. Thank you, Professor Prabhakar. I'll clap. We can.
And this was a good discussion.
Yeah, thanks. All right, so I'm gonna let Chenglu take over to introduce our next speaker.
Yeah, cool. So our next speaker is Professor Bo Li. Professor Bo Li is an assistant professor in the Department of Computer Science at University of Illinois at Urbana-Champaign, and is a recipient of the Semantic Research Labs Fellowship Rising Stars MIT TR35 and the Best Paper Awards in several machine learning and security conferences. Previously, she was a postdoc researcher in UC Berkeley. Her research focuses on both theoretical and practical aspects of security, machine learning, privacy, game theory, and adversarial machine learning. She has designed several robust learning algorithms, a scalable framework for achieving robustness for a range of learning methods, and a privacy-preserving data publishing system. Her work has been featured by major publications and the media outlets such as Nature, Wired, Fortune, and the IEEE Spectrum. And The title of the talk of Professor Borley is End-to-End Robustness for Sensing Reasoning Pipeline in Adversarial Environments. And let's welcome Professor Borley to give us a brief recap of her talk. Cool.
Thank you. Yeah, thank you for the nice introduction. Let me share my screen this way. So yeah, so okay. So I will give a brief introduction for this talk, and actually I include three topics I think are related and interesting. So I will briefly give some summary for them, and hopefully it will help for the understanding of them. So basically here I want to mainly either promote or introduce this end-to-end robustness for sensing reasoning pipeline in adversarial environments. And the motivation for this whole topic or area of work is that we know there are a lot of adversarial behaviors in real world against the machine learning or AI systems. And this is an example that a lot of people like to use, is that if we make the small manipulations in the physical world on, say, put some stickers on the stop sign with specific design and optimization for the colors, positions, and shapes, and then surprisingly, all the stop signs here can be misrecognized as a speed limit sign 45, which is the adversarial target for a wide range of neural networks. So this has raised a lot of severe concerns about the safety for real-world machine learning systems or AI deployment. So in this talk, I actually mainly want to emphasize from three perspectives to try to see to what extent we can verify the safety of machine learning system, and what's the potential other additional information we can leverage in terms of improve the certified robustness of a machine learning model. So the first one I want to briefly introduce here is that we have certified a lot of single neural network or ensemble neural network models, but here I want to introduce a new perspective about machine learning model pipeline, because in practice, as we like industry or in practice, as we do a machine learning, deploy a machine learning system, it's actually very hard for us to only rely on one machine learning or deep learning model to make the decision or prediction, right? So essentially, we can combine the things together and incorporate human knowledge to help improve the robustness and eventually certify the end-to-end robustness of this pipeline instead of for a single, say, neural network. And this pipeline looks like, from this small figure, hopefully you can see clearly, or we can go to next slide first. So basically, here on the sensing component, there are several say neural networks, and they are in charge of different functionalities. For example, they are recognizing different objects within an image, or they are recognize different, say, road signs on a road, or recognize pedestrians. And then the sensing component will connect with another reasoning component, which we actually realize that with graphical models, for example, Markov logic networks or Bayesian networks. So in this graphical model structure, we will incorporate knowledge, meaning those knowledge will be expressed as logic rules. For example, if a dog is if object is a dog, it should be an animal as well, such inference. So the graphical model will allow you to make the inference, and then the goal is to certify this end-to-end robustness, meaning we can see on the first component, on the sensing part, this is exactly currently what we are doing for certifying the robustness of single neural network models. For example, we have good strategies like randomized smoothing, interval propagation, and other strategies to certify it. But as long as we can certify this component, we can go to the next. And the interesting part is that for the reasoning component, because it's a graphical model, so the weight is non-negative, and there are some good structures for it, even though the factorial reasoning can be Sharpe complete. And here, because of some structures we have, we can actually solve the min-max problem for this reasoning component and certify this the robustness for this component as well. And then by combining these two components together, we can have the end-to-end certification of the robustness for this whole machine learning pipeline. So that's a brief introduction for this, and hopefully that can give us a new a view of what can we guaranteed in real world for the robustness of machine learning models. And back to that, the second thing I briefly introduced is because we have this sensing reasoning pipeline, so a lot of people may ask where the knowledge come from, right? So usually there are some common sense and we can leverage. For example, in ImageNet, there are some hierarchy knowledge about which animal belongs to what categories. So leveraging this, we can build up this graphical model. But for a lot of other domains, there are no such ready to use knowledge. So how we can gather those knowledge? So one perspective is to use the game theoretical analysis to make interactions with attackers so that we can understand what's attacker cost function, utility function, and what's their intention, so as to improve or certify the robustness of this decision making based on the understanding of the attacker behavior. So basically, the attacker behavior will be the constraints, and the objective function is the defender's objective, which is the robust classification or robust decision making. So by this solving this constraint optimization, it is possible to improve the robustness guarantee for a machine learning pipeline or machine learning process. And regarding this game theoretical analysis, which still use some external knowledge or information, the next information I want to, which is a third topic, is whether there are some internal information or intrinsic information within data or machine learning model that we can leverage. So basically here I show if there are some adversarial behaviors. For example, if you add some noise to the image or to the NLP data, actually naturally there are own intrinsic structures, for example, spatial consistency, temporal consistency, or even task consistency. Some types of intrinsic information can be broken. And by verifying whether those internal or intrinsic consistency information have been broken, it is possible to identify whether there are some adversarial behavior happens. And this is to say, by combining the extrinsic, intrinsic information, it is again possible to improve the robustness guarantee for a machine learning pipeline or system. So there are some concrete results for each of this information, and they kind of add more and more information to the machine learning model that we want to certify, so that eventually we can actually combine all information we can collect together to get the end-to-end robustness guarantee for a given machine learning model. Yeah, and this is main overview of the talk, and there are some details for each one, and if we have any questions or discussions, we can discuss in detail then. Yeah, thank you.
Good, thank you, Bo. So while we are waiting for questions from the audience, I will start with the questions that Taylor and I prepared earlier. The first question is, in your first part of the talk, you're talking about building this ensemble networks in the sensing reasoning pipeline using some knowledge. Can you describe how can you leverage your knowledge in choosing those ensemble networks?
Yeah, sure. So here, for example, in these slides, there are some like input, which is a sensing model here. For example, each sensing model is in charging of predicting whether this image is a dog or it's a cat or it's an animal or not. And then these are the binary output with probability. So this probability will send to the reasoning component, and each reasoning component here will form actually a factor graph. So each factor represent a knowledge, which is first order logic expression. For example, if like say a dog, if the instance is a dog, it should be an animal, then this a regular expression will be expressed in this way and in this factor. So by building up this factor graph, we can automatically learn the weights so that example is that if the sensing model tell us this is a dog, but then this sensing model tells us it is not an animal, then by combining these two logic form, we can see either of these sensing model definitely have some misclassification or made some errors. So in that way, we can come back to fix the errors made by each sensing model by leveraging this knowledge we have, so that it will essentially improve the confidence of the certain prediction and correct made by some sensing models here. So the high-level assumption is that it is impossible for attacker to attack all the sensing models altogether and also satisfy the knowledge here. So that's why the knowledge here will be helpful to improve or help correct the mistakes made by part of the sensing models.
Cool, thank you. And we have a hand raising from the audience. Anna, I'm going to unmute you and you can ask the question.
Mm-hmm.
Oh, thanks. Thank you very much for the talk. Can you hear me?
Yes.
Okay. Maybe it's a bit a technical question, but in your extended presentation, you mentioned that if you have several instances of the attacks, you can cluster them according to maybe a set of goals that the attackers had. And I found that very interesting idea. And then you can optimize for representative instance of each of these goals when building your defense. So yeah, that's exactly
this part, right?
Yeah. So my question was, how exactly do you have an efficient algorithm how you find this kind of representative instances? And if you use a game theoretic approach, can the attacker somehow misuse this information as well to build the attack even stronger?
Yeah, thank you for the question. Yeah, I think that's very interesting question and very important. So I briefly say we cluster here, but actually it's very data and task dependent. For example, in this example, it's a spam classification. So if it's a spam, we can cluster them in the semantic space. For example, one interesting thing is we can naively use, say, Euclidean distance for the embedding space of each spam, right? And then cluster them. But that is very rough, as you can see, and the cluster algorithm can be evaded by the attacker as well. So one thing is there are some low-level semantic space that is hard to evade, which means if we get the bird embeddings for the NLP instances, and then when we cluster the word instead of each individual sentences, those words actually naturally form some clusters which have some semantic underlying meaning, which is very interesting that we find if we have a cluster, the center is, say, a car, and we have another cluster, the center is an airplane, and in the middle there is some like motorcycle or something. It's kind of like in the semantic space, they know the motorcycle is like in the between of a car and the airplane. So I mean, these types of semantic representation is very hard to invade because it's based on the semantics within each sentence. So this way, we first cluster the word together based on the environment of each sentence, and then we make sure the clusters of the sentence are concurrent and consistent with the word cluster itself, which have this constraint from the semantic space, so that the assumption here is attacker have certain common goal, which is the adversary, they either want to say turn advertisement in a spam email to look benign, but it will still have the flavor of the advertisement so that human can buy something. So in this case, the underlying semantic space should be still advertisement. It should not change. So by checking this semantic change, we can make sure those clustered goals still are satisfied as adversary goals, and ensure that these clusters didn't change much by manipulating certain words within the emails. Yeah, did that answer the question? So basically, the way we are doing is we cluster the words together first, and then cluster the sentence, and then compare the two types of clusters and ensure that the semantic are aligned with each other. Yeah.
Cool. So I guess the next question from our prepared pile is, how does this game theoretical defense compare with other robust learning approach, such as convex defense by computing the dual and convex approximation of a robustness problem? I think that is introduced by Zickel-Kauter's group. Can you briefly talk about that?
Sure. I actually haven't directly compared with the interval network yet because it's a new one currently, but we compare with, say, just IBP, and so it's, for example, compare with randomized smoothing. It's a different types of generation, because randomized smoothing actually ensure the consistency of the prediction, but we don't know what's exactly the adversarial constraint. But here, one advantage is that it may allow larger radius compared with current one, because current one actually assume it's make a more like a strong assumption, not actually a weaker assumption for attackers, meaning attacker can do arbitrary things as long as they are within certain magnitude radius, perturbation magnitude radius, right? But here we assume that we hope we can certify larger radius, but we give some constraints to the attacker because we assume the attacker has this much budget. As long as they finish this budget by, say, manipulating how many words or manipulating how many, what's the radius of image, then they cannot go further for that. This gives a opportunity for, say, important sampling, that I don't need the whole radius to be certified, because the assumption is that for certain radius, it's more important. Like as an attacker, I really want to manipulate my cat to a dog, but I don't care if a cat belonged misclassified as a monkey or not. So in this way, I can certify a larger range along the direction from cat to a dog, but not the other way, other directions. So this way, it's on one hand, give you some larger ability to certify a larger radius along certain directions. But on the other hand, it also make additional assumption about what's the attacker's goal and what attacker's behavior from this interaction with the attacker as a game theoretical analysis. So I would say on the same radius, they will perform similar, but under other different assumptions that we give more assumptions for the attackers. This will, the game theoretical analysis will be flexible as adding additional constraints to solve the constraint optimization.
I see. If I can interpret this as a way to bring in your prior knowledge or semantic knowledge to the problem.
Exactly. Yeah.
Cool. Cool. Thank you so much. I think we are out of time. So although we still have a few questions, but maybe we can discuss the questions offline. And thank you so much. And this concludes our invited talks. And we can move on to the contributed talks. So Taylor, would you like to take over on the first contributed talk?
Sure. Thank you. And yes, thanks again to our invited speakers. We're, I'm sure, all clapping, but almost everyone's muted, so I'll give it a little. Our first Q&A session for the contributed talks is on the paper Image Approximation for Feed-Forward Nets. And I believe Eleonora Pipia is the one who will be speaking. So you should be able to unmute yourself and share if you want to share any slides.
Yes, so good afternoon. Yeah, let me see. You should see the slides.
Yep, and we hear you fine. So
okay.
So if it's just a short intro, and then we'll ask questions.
Yes, just 4 slides. So this is a joint work with Professor Taudang and Professor Alberto Policriti. Yep. You should think of this work in the context of closed loop with a neural network that plays the role of the controller, so neural net control system. And in this case, there are a bunch of tools that already examine the closed loop verification problem, but the main goal here is to be able to approximate the behavior of the neural net. So the problem that we address is to over-approximate the behavior of the neural net, and the plan is to address this problem using the Bernstein expansion, so the Bernstein theory for the polynomial function. So in particular, we focus and we work layer by layer. So consider a neural net N with N input and M output, and an input set defined with a set of linear constraints. Then we need to be able to propagate this constraint layer by layer. And yeah, in general, we can split the two main part of each neuron. The first one is linear, is an affine function, and we are able to propagate the constraint through this function. But then we have the activation function that is in general nonlinear. So we remain with a set of nonlinear constraints. So in general, we have a set of nonlinear constraints that links the values at the preview layer, so x to the L minus 1, with the values at the current layer, so x of L. And what we want to do is approximate, over-approximate this set of constraints, in general, with a set of linear constraints. Could be an hyperrectangle, but in this case, so bound the value of each neuron, but in this case, we lose the input-output relation, or could be through a polytope, so maintaining the input-output relation. In particular, with the Bernstein theory, we can obtain through a rational function or a polynomial function, we have a really interesting property on the coefficient on the Bernstein expansion. With the rational function, so if we approximate the activation with a rational function, we can take the maximum and the minimum Bernstein coefficient, and we can bound with an interval the output values. So in this case, we can bound just with hyperrectangles. But if we approximate the activation function with a polynomial function, then all the Bernstein coefficient, if we link with a convex hull, we can bound with linear constraints, so with a polytope, and we can maintain the input-output relation through the layers. And moreover, what we are in the end interested in is approximate with a piecewise polynomial function in order to also reduce the degree of the polynomial and maybe take a constant value when the activation function is more flat. And in particular, in this work, we focus on the first part, so approximate an activation function with a rational function, and so obtaining a bound that is an hyperrectangle. This just for a first start with also a feasibility analysis to understand if this approach could be feasible in general. And then we are working and trying to go ahead with a polynomial function. So yeah, I can stop here.
All right, thank you. Any questions from our audience? I'll start with one while people may be thinking that we had prepared in advance. So you kind of just talked about it a second ago, but so from what I recall, the results were applied to the hyperbolic tangent activations, but you discussed some of the background theory of how it could be applied to others. Could you talk about that, whether you have any results so far in that direction for trying to use this in others?
Yes. But basically, okay, we cite also in the paper a result that proves that we can approximate also the sigmoid and the ReLU with a rational function. In general, all the works and our algorithm works in the same way because the Bernstein is not related to the shape of the rational function that we choose. Also for the hyperbolic tangent, we can change the rational function. What we need to look at is the denominator. That is where we need to put more attention, because in order to bound the output of a rational function, what we need to guarantee is that the Bernstein coefficient have all the same side, the Bernstein coefficient of the denominator. So we take the hyperbolic tangent as a case study to go in detail on the step. If we change the rational function, what we need to do is look at the denominator, see where there is the maximum and minimum, and in case split the domain. So split in order to guarantee this property and be able to apply the Bernstein range enclosing property, but the rest goes as the same.
Okay, I don't see any hands raised or any other questions from the audience, so I'll ask another. So the Bernstein polynomial approaches have been used a fair amount in hybrid systems verification. And I know you mentioned that's sort of part of your goal is to get toward closed loop verification. So do you have any results in that direction, or any plans, or what the approach might be towards combining this image approximation method into the closed loop?
Yeah, we don't have a result yet. We are working on it. The idea is to obtain in the end a set of relational constraints to so this approximation in the end is a relational approximation from the input to the output of this neural net. So in the closed loop, you will substitute the role of the controller with a set of relational constraints. So this is the idea. So you will start with a closed loop, you will reach an input set that should be entered to the neural net, and the output will be the set of constraints that bound the behavior of the neural net.
All right. Let's see. I'm just checking all of our sources of questions since we aren't completely consistent. But I don't see any, so I'll ask one last quick one because we're almost out of time. So what's the advantage of the Bernstein polynomial approximation over other methods that might be used, like Taylor model approximations?
But the real advantage, in principle, they all can approximate really well, increasing the degree of the function the polynomial function that we choose. Also here, if we increase the polynomial expansion. What we think is really useful is the part with the convex hull. So be able not just to use bound that here we use it for the rational and we are forced to use it, but the next step with the polynomial function, we want to use again the convex hull. So be able to use the convex hull, reduce a lot the error that we commit in the end, for sure.
Okay.
And yeah, with Taylor, if I remember well, it's just with hyperboxes.
All right, thank you. So I think we're out of time for that, but thank you very much. So Qinglu will go to the next talk.
Our next talk is by Stanley, Execution Guided Over Approximation for Improving Scalability of Neural Network Verification. Stanley, would you like to take over?
Yes, can everyone see my screen?
Yes.
Okay, great. So I have 2 slides just to review the talk. So this talk, what this is about is the neural network verification problem in the open loop. So given a set of inputs, what possible outputs are possible. And so I had a talk in CAV a couple hours ago talking about 5 or so optimizations for exact analysis that can improve the scalability of start set verification methods by 10 to 100 times sometimes. And so that was for exact analysis. For VNN comp, the neural network competition, we used a method that used some exact analysis and some over approximation. And so for over approximation, it's sort of the same situation. There's probably 5 optimizations that we used. And so one of the more interesting ones was this one, which we call ego. So the way to think of ego is as sort of a competitor to Segar analysis. So when we're doing exact analysis of ReLU networks, as many of you know, it becomes sort of a search problem where you can imagine if your neurons are ordered in some fashion, you can choose for each neuron whether to split it into 2 cases or to analyze it using an over approximation. And so this partial over approximation approach, you can use a Segar sort of setup where you first use the coarsest over approximation, and then if that doesn't prove the property, you refine it somewhat by, let's say, splitting on the first neuron, and then you have now 2 sort of subproblems you need to solve. So it sort of becomes a tree search. And so that's sort of what's shown here is on the right-hand side, you see sort of this tree where the root of the tree would be, let's take every neuron that potentially splits and consider over approximating it. And so in branch and bound methods, this is sort of equivalent to like a linear relaxation, you could think of it that way, of the MILP problem. That's another way to think of it. So the Segar order would first try the coarse over approximation, then it would refine, try a slightly better over approximation, then it would refine. And then let's say you get to node 3 and you try an over approximation at this point and it can prove the property is safe, then we would sort of have to go down the other branches. And in this case, we're doing like this sort of depth first search strategy. So the next node it would check would be node 4. Ego, which is execution guided over approximation, tries a different approach. So what it does is it first executes a concrete system. So it sort of goes down all of the branches until there's no more branching that's possible. And it first tries to verify node A. And if that succeeds, it'll start to do over approximative analysis as it pops node off of the depth first search queue. So the next node it would visit would be node B, and it would try it with over approximation. You could prove the property, and then it would be node C. You try it with over approximation to prove the property. And then finally, you arrive at the same node that you arrived in Segar at node D. And so you sort of got to the same place, but you visited nodes in a different order. And sort of the claim is that in certain cases, this ego order is more efficient. It takes less time to verify than doing things in the Segar order. And so this is a general search strategy, not just for neural network verification. But let's look at sort of a concrete instantiation of this in the neural network case. So this is the ACAS-XU benchmark, which I think Taylor will get into the results later during the VNN comp. But for property 9, which is this sort of a difficult property here, we can look at what the search tree looks like using the Segar search order and using the ego search order. So using the Segar search order, you can see like line 1, there's no pluses here. So this is really the root of the tree. So this is analyzing all of the possible splits in the network. And there's 201 possible splits, and it takes about 3 seconds to do this type of analysis because you have to solve a lot of linear programs, at least in the star set based approach. And then you can't use it to prove the property. So you have to go down one of the branches. And so you end up going down several of these branches before you get to a case where the property is proved. And then of course you would try the sort of other branches. But the point is in lines 1 through 6, these take a lot of time, 3 seconds, 2 seconds, 1.3 seconds. And you kind of throw away the result because you can't prove the property. In the ego search order, the first thing it does is it goes down a concrete sort of set of splits, and it can prove the property is safe, and it takes a very quick amount of time, half a millisecond. And then iteratively, it sort of backs off the search tree doing over approximative analysis until it arrives to sort of a very similar state. And so it actually ends up looking at more nodes, but each of these nodes verify very quickly. So milliseconds essentially to the search instead. So for this particular case, looking at just this optimization by itself, ego ended up being a faster approach too. So, and you can see that, if we want to prove this property in like 2.5 seconds, even doing a single full over approximation with the Segar order, you sort of will take more time than doing that. So you really need better strategies. And so this is one instantiation, but also everywhere you use Segar, you could maybe consider using ego too. So something like software verification or hybrid systems analysis, you could have the same thing where doing full over approximation, maybe there's too much branching, there's state space explosion. So ego maybe might be a better strategy too. So that's the overview. I think there's a longer version online if people are interested.
Cool, thank you. And we'll take questions from here. Please enter your question in either in the chat, or if you're on the live stream, you can enter it on YouTube. We're monitoring multiple channels. And I will start with one prepared question, which is, does the computation efficiency introduced by ego depend on the network structure? For example, the width and depth of the network?
Yeah, so it's sort of interesting, the trade-off. So you can always get to a concrete execution pretty quickly from what I've seen, but sometimes it's there's a lot of branches you need to go in, especially if the initial set is large. I think for all of the methods, whenever there's a lot of branching, that causes problems, and so ego doesn't really solve that problem.
So if I interpret this answer, that's the key factor that affecting the efficiency is not the width and depth of the network, is how many branches we have in the network.
That's what I would say is the case, and maybe it depends on other methods, but since especially like the star set method, well, when you're doing exact analysis, you enumerate all the branches, so that's the most important factor. And so with partial over approximation, you skip some of the branches, but it's still a major factor.
I see. And is there any result to show the relationship between the computation efficiency and the number of branches?
It's a good question. So I don't think so. So it's hard to compute exactly the number of branches if it becomes too large, right? So I think for a lot of the like MNIST and CFAR networks that people analyze, there's no way to even know what the exact number of branches is, because if you can run it for a couple of days and then give up, and then you can maybe get a lower bound. But it's an interesting direction if you could prove something more theoretical. Maybe for exact analysis, of course, right? Because it's gonna you need to at least visit each branch once, each path once.
Yeah. For example, if your input set is bounded, then probably you can try to compute how many branches are there corresponding to your bounded input set.
Yeah, a lot of it will depend. So for any bounded input set, I can construct a neural network that has really bad branching, right? I can just scale everything down. So your bounded set becomes a very large set relative to whatever how the network splits. So I mean, it's worst case exponential, but that's not a great bound.
Cool. Let's see. Is there any question from the audience? Okay, I see one. Wow, long question. So Serge, do you want to ask the question yourself? I can unmute you. Okay.
Hi, can you hear me?
Yep.
Yeah. So thank you for the presentation. I was just wondering what happens when you run the ego, when you go back up to the root. If the first layer has more than one value that needs to be split, do you just choose a second one and run again ego, or use over approximation on this second one?
Yeah, so the search order, it's you sort the neurons in some order. So the easiest order is just the order in the network. So there's 5 layers, and then each layer there's, let's say, 50 neurons or something like that. And so there's some ordering, and then you find which ones can split. And so let's say layer 1, neuron 1 is the first one to split. And so that in this tree, you can imagine that's the root of the tree. And so if you split, then the second neuron that you split on will be the next one after layer 1, neuron 1. And it'll depend, right? So for maybe for the left branch and the right branch, these could be different depending on how the splitting works. So if there's another one that's split, it'll just be the next one in the ordering. I don't know if that answers the question. Oh, I think, are you muted again?
Yeah, maybe he's muted again. But since we're out of time, maybe we can keep the discussion offline. Oh, Serge said yes, it does answer the question. So let's now move to the next speaker.
All right, then thanks, Stan. We're all clapping, I'm sure. So the next Q&A will be for the paper Property Inference in ReLU Nets using linear interpolants. And I think we have a couple of the speakers here, but I think Jatin is going to give the quick overview, and then we'll open it up to the Q&A.
Hello, everyone. So in this work, our aim is to identify a subset of the input space that implies a property. For now, we are only restricting ourselves to convex subsets, but we may be able to generalize these things further. So the idea is that you're given an input property P, which is the goal property, and you want to find out a convex region such that every point in that region satisfies that property P. Our key insight to solving this problem is to use an interpolate property I. So the goal property P is generally specified at a high level. It's some specification which we want out of the neural network, but it does not necessarily make use of the structure of the neural network. So what we do is we introduce an interpolate property I, which is more low level than P, and we try to find convex regions which satisfy I instead. Once we have a convex region which satisfies I, we use I to reason about P. And like how this is done is a little technical, and we defer this to the actual talk. But the idea is there is a level of indirection when you're trying to find convex regions, and you can use a low level property to get a larger input space. So our main decision procedure looks as follows. We are given an input property P. We are given a neural network, and we are given this convex region sigma. Like sigma is represented using some activation patterns and stuff, but I'm not going to get into that. So there's some convex region sigma. And now I check if sigma implies P. If sigma implies P, then I'll try to minimalize sigma. I'll try to like make it larger using something. And if it doesn't, then I just return an intersection of the points that satisfy P. So instead of doing this, what we propose is you forget about the property P. You consider the interpolate I, and you check if sigma implies I. And if every point in that convex region sigma implies I, then you try to add more. You try to make the set larger based on I, and then you use I to like represent P. So we believe that this process of enlarging the input convex region is better suited if we use the property I instead of P. And we give details on how one can do this in the actual talk. If you have any questions.
Okay, thank you. So we'll continue monitoring our various channels, but I'll start with one of our prepared questions. So in the full talk, I looked, if I recall, I think it was this diabetes data set. And it's kind of a small network. So could you talk about how maybe to scale this up to larger networks and potentially more complex properties than what you looked at as well?
Yeah, so the scalability, actually this work is based on an earlier work by Corina and like by Divya Gopinath. They did this, basically did this analysis for larger networks and that scale. So like there is no reason for like no scalability of this procedure because it deals with convex regions at the level of activation patterns. And they have a very nice algorithm to like scale for to scale for large networks. The second question is talking about more complex properties. That is something that we haven't explored yet, and like it's interesting, like if we can find interpolants that can be used for complex properties, like that is future. But the scaling for large networks of this technique is like tested out in prior work. So I think they implemented it on Akashu networks and other things.
All right, thank you. Let me just make a quick scan around. I don't see any from the audience. So I can ask another. I mean, this can be sort of a very general question, but I'm curious as to how it applies in the context of this framework of interpolants. So could you talk about the relationship between the interpolants and trying to do proofs by inductive invariance, if you're familiar with that?
I am a little familiar with that, but I believe inductive invariants typically imply the property that you're trying to satisfy. Like I think you add, so you maintain this invariant, maintain the fact that at each step your interpolant implies the actual property P that you're trying to satisfy. Here that is not the case. Here all we are saying is if you know I, you can reason about P within some constant time. So if we have the property I, then we can check P easily. And that's all we're saying. Here I does not imply P. So this is like a little different from interpolation in like the more traditional sense, where you have that the goal property is always implied by the interpolant. It's I is typically a larger set. The set of points that satisfy I is typically a larger set than P.
Okay, thank you. Just checking again. Let's see. I don't see any others, so I can ask another. So I didn't earlier catch this other related work on ACAS-XU, but I guess do you have any thoughts about how this method could be applied to other verification problems? So lots of people are looking at adversarial robustness, for example. So when you have that, your setup is a little bit different often because you have this auxiliary input, which is the image, and then you're creating you're kind of bloating the image in some way to create a set of images, and then trying to do some evaluation of all of them. So do you have any thoughts about how this type of methodology might be applicable for those kind of classification networks and things?
Yes. So in that case, your property P would be something like the outputs y0 and y1 are such that y0 is greater than y1. And then you're given an input point. You start out with the activation pattern which contains that input point, and find all the neighboring activation patterns which are only epsilon away from that input point. And then you try to generalize that activation pattern to those. If you fail to generalize, you can get a counterexample. And if you don't, then you have satisfied like all the neighboring activation patterns. You have made sure that all the neighboring activation patterns which are within epsilon distance satisfy P. I think there is an upcoming work that actually does this exactly. So I mean, it's under review. So but there is one work which is doing exactly this.
Okay, cool. That sounds promising. Well, if I look at the clock, I think we're about out of time. So thanks for the presentation and answering the questions. We're all clapping, so not just me. Okay, so I'll let Cheng-Lu take it back over.
Cool. So the next paper is on the effectiveness of L1 norm-based channel pruning for convolutional neural network verification. The presenter is Diego. Hi, Diego, you can take it from there.
Hello, can you hear me?
Yes.
So yeah, I'm Diego Montana from Vanderbilt University, a student with Taylor Johnson, and I'm going to talk about the effectiveness of L1 norm-based channel pruning for CNN verification. I think I'll just do it like this. So we have some trained convolutional neural networks. We have 4 of them: VGG 11, VGG 13, 16, 19. So the VGG family of convolutional neural networks. trained on CIFAR 10. So the goal of this paper is to evaluate how one pruning technique that focuses on pruning the channels of the convolutional neural networks affects the verification of this neural network. So we use the NNMV, the neural network verification toolbox written in MATLAB, which was presented at CAF by Tran. And so what we are trying to aim is if correctly classified image, like an airplane, for example, gets some perturbation, can we still verify that the neural network will correctly classify this image as an airplane? So in this case, we use the brightening attack, which consists on converting certain pixels that are above a threshold into the brightest possible values. So we create a small set for these pixels and use NNV to see if the networks are robust to this perturbation or not. We use the image star set representation, and we use over approximation methods to analyze these networks. So we have 3 different experiments. For the first ones, we allow up to 400 pixels to be perturbed. For the second one, we try to minimize the input set to be small, so we only allowed a maximum of 50 pixels to be attacked. And for the third one, we want the number of pixels to be between 20 and 80. So we can see in experiments 2 and 3 some results that we will expect to see, such as like the verification time is shorter for the smaller networks than for the larger ones, similar to their experiment. However, we see that not in all the cases it's like that. So for experiment 1, actually the smaller networks take longer to analyze these larger input sets. And yeah, that's the brief overview from our work. Any questions?
Cool, thanks. While we are waiting for questions from the audience, I will start from a prepared question. So in your result, it shows that the performance of the, basically the efficiency of computation for verification using NNV does not improve after you prune the neural network. Is there any insight on why this happens? And is this result unique to reachability-based methods?
I don't think it's unique to reachability methods. I think it depends also on the pruning techniques. There are some pruning techniques that can create a sparsity on the neural networks. So some satisfiability can take longer from reduced size pruning technique, pruning neural networks. But in this case, this time increases a lot, especially when the input set, so the number of pixels is very large, but it doesn't happen when the input set is smaller. So I'm not quite sure. There's only like, in these 96 images, there's only like 4 or 5 images that take about like 90% of the time. So I couldn't tell you if this will always happen or if this is mainly from these specific images. There's not a certain conclusion that I can give you right now, but it's something that we're looking into, and we're working with our techniques and other images to evaluate if this will usually happen with certain techniques, pruning techniques.
Cool. Can you discuss a little bit more about your plan to analyze this problem further?
Yes, so one way will be to see which layers are taking the longest in the reachability analysis. So it might be because the weights are in general larger, and this causes the reachability analysis for the ReLU layers to have to do more splits. So in this case, it's the over approximation technique. So we'll have to add more variables to the image start set, and that might cause these few images cases to take exponentially longer than the other cases. I also want to look into other attacks and a few other pruning techniques. Like there's one by Renda et al. That looks into multiple pruning steps. So instead of just one step, it prunes to smaller and smaller neural networks. That it was published this year at ICLR. And so there are a couple of other techniques that I want to see on how these reachability analysis methods apply to those networks.
Cool. Let's see if we get any questions from the audience. Yeah, I didn't see any. Yeah, maybe I can continue with my question. Yeah, another question is how, so you also mentioned in your answer to my previous question that the conclusion you draw from this paper highly depends on the data set you're using. And is there any insight about, suppose you work with a different set of image classification problem, how that will change the conclusion of your paper?
I am not sure about if the data sets will change much. I mean, I think, for example, for an image data set like the ImageNet, it will be harder to prove the robustness since there are 1,000 outputs. So you will have probably more intervals that intersect with each other to prove that the neural networks are robust. But with respect to time and the prune techniques, I'm not sure if that will affect too much.
Cool. If there's no more questions from the audience, then thank you, Diego. I think that concludes our session for contributed papers. Thank you.
Okay. Yep. Thanks, everyone. Thanks, Diego. So what we'll do now, I have some slides prepared on the neural net verification competition, VNN comp. So let me get everything set up. Okay, we see my slide.
Yes.
Great. And okay. All right, so I'll get started. Okay, so so we organized a competition on neural net verification. Everything was conducted sort of asynchronously. We're in the process of creating a report from the competition. This QR code will show up a few more times, but if you want to look at a read-only version of the report, that should go to it. So just as an FYI, there was just a little lightning nearby. So in case this goes down, just to be aware. it seems okay. So just a quick overview of why we tried to do this and some of the mechanisms. So competitions and challenges have helped advance various CAV-related domains as well as machine learning domains. So some of the CAV examples would be SMT comp, the software verification competition, SV comp, the hybrid system verification competition, the satisfiability competition, and then there's a slew of others. Within ML as well, there are a variety of challenges and competitions, often focusing on trying to get the highest accuracy of, let's say, image classification would be a common one on a particular data set. So we wanted to give this a try and try to foster a variety of goals that I'll discuss in a moment within the VNN community that's sort of been emerging over the last couple of years. So within this iteration, we modeled this after a competition that some of the organizers had familiarity with, which is the hybrid system verification competition, which is sort of more of a challenge and a friendly competition that's often held with CPS week, but sometimes with CAV. And if you're interested in that, you can find more details at the website. So I mentioned within that competition, there is a category for doing closed loop system verification. So there's an AI in NCS category where you'd have neural networks in closed loop. So with a plant model and trying to do verification of those types of systems that were talked about a few times by some of the presenters in VNN today. So that's now in the second iteration that finished up a few weeks ago. So some of the goals of trying to do this was to get the community involved, try to get some standardized benchmark problems and formats, identify issues for creating interchange standards. So there's an effort underway within this community to create a standard VNN lib, which I'll talk a little bit more about later. And that we got an update on at the CAV Foamless workshop on Sunday, this past Sunday. So, and overall trying to get to being able to interchange models, identify limitations of methods, pros and cons, and then eventually, not in this iteration, but eventually get to apples type of comparisons. So this year, it's fair to call it sort of a challenge instead of a competition. So this is just an overview of how things were organized. So we started organization around February timeframe. If you're interested in this kind of community, there's a listserv that prior VNN organizers had put together. So related announcements show up there. We had discussions on competition categories and candidate benchmarks on GitHub, initially through a GitHub team discussion and then through issues, just because that the mechanism for that was a bit better and it allows us to archive things more easily. So through that, we came up with 3 categories, primarily based around the architecture of the neural nets and what types of activations they would have. So the 3 categories were CNN for convolutional neural nets, PWL for feed-forward networks with piecewise linear activation, so ReLUs, and NLN for feed-forward networks with nonlinear activations, so particularly TANH and sigmoid. So we finalized the benchmarks in May and June timeframe. We used ONNX models, and part of the reason for that was that's what the VNN lib folks are from that near the end. So then we've been in June and July executing benchmarks, submitting results, and doing report generation. So before COVID, we had a whole lot of interest, and we still wound up with a good amount of interest, I think. So obviously everyone's schedules became very hectic, and not everyone who initially indicated interest has submitted results, but I'll talk about some mechanisms for how we may facilitate that in the future. So there's a list of these on the VNN website, so there's a fair amount of tool development ongoing within the community. So then we had kind of another round of indicating what categories participants would be interested in, and this is how it came down to look. So the most interest was in the piecewise linear category, and a lot of overlap between those tools and the CNN category, and less interest within the nonlinear category. So a lot of tools don't support some of the nonlinear activations like TANH. So then this is sort of the status of who's submitted results so far. So I think overall it's about 8 or 9 total teams because several teams and tools participated in multiple categories. And this is just a list of the people who were involved on each team. And I'd like to thank all of them. I'll thank them again later, but there's a lot of effort to try to do this, particularly the first iteration with things, not knowing everything about the process and just trying to kind of get this kick started and off of the ground. So I really appreciate the involvement of all of the participants. So I'll tell you a little bit about the benchmarks and some of the results. So within the categories, we did kind of a back and forth of coming up with benchmarks and how things ended up. Within all 3 categories, we had image classification benchmarks, looking at local adversarial robustness, primarily on MNIST and a little bit on CFAR. In verification benchmark instance consisted of a network, a robustness bound, and a timeout as well, as well as how things should be classified, since these are all classification networks. So the networks varied in numbers of layers of neurons, and the number of images that were evaluated on varied, but typically, depending on the particular network and data set, somewhere around 25 to 100. Within the piecewise linear category, we also use the ACAS XU networks, all of them and all properties. So most of the timeouts were 5 minutes, but some were harder instances. And so all these are available on the competition repository. So I'm not going to talk about all of the networks in too much detail, but just to give you a sense of how things varied. So this is the piecewise linear MNIST classifier networks. So the numbers of ReLU layers varied, I believe 2, 4, and 6, and some other variation. Within the CNN category, again, some variation in numbers of layers and things. So some of the benchmarks, and this is discussed in the report in more depth, but some of these did use some defenses to adversarial perturbations. All right, so then CFAR networks. And the nonlinear feed-forward classifiers, again, sigmoid and TANH, and again, varying numbers of activations and layers. Right, so the process that we went through, participants submitted pull requests to the GitHub repository with ideally a Docker file, but an installation script of some form, and then a script to reproduce things. And then participants added their results to the report. I'll talk just briefly about the results, and then we'll get into some discussion. So just one thing to note, so we did not use standardized hardware in this iteration, in part from the time frame and how chaotic the world has been since we started trying to do this. So the participants ran things themselves. So you need to interpret the results with this as the hardware varied. Some participants were using sort of a typical desktop, whereas some participants are using cloud computing. One group their method does use GPUs, so that's something to be aware of as well. So trying to do exact comparisons with that would be something we'd want to discuss in more depth. And then not all the participants submitted results for all the benchmarks yet, even for those who did go ahead and submit some results. Particularly some of the CFAR networks. We prioritize the MNIST ones just in the interest of time. Right, so how does some of the results look? So this is a form of a cactus plot, so I'll just tell you how to interpret this. So this is on the ACAS-XU, the easier variants with the 5-minute timeouts in the piecewise linear category. So being over here is good on the right side where you've checked all instances within the 5-minute timeout. Right, so being down in this region is sort of optimal. So what we can see from what was available so far in an enum, which Stanley Bach talked a little bit about earlier, some of the methods that he's using to do optimizations was quite effective on these. And within the timeouts, I think was the only tool that verified all the properties. So that's interesting and probably motivates others exploring some of the techniques that are used within that. And then the others, I think everybody verified at least about half of the networks and properties within the timeouts. So the harder instances, this was with the 6-hour timeout, and all these times are in seconds. So again, in an enum was the only one who was able to verify all of them within that timeout, and many of them in not that much time. All these times are in seconds. And then none of the other participants, I suppose, were able to do that. But again, motivates some various improvements probably that can be made in some of the tool methods. So moving on to the MNIST image classifiers. So again, looking at local adversarial robustness. So this was using a 15-minute timeout. So some of these were harder, as we can see. No tool verified all of these within the timeout. And overall, you know, things are sort of distributed reasonably close together for these. And again, just as we mentioned earlier, all this has to be interpreted since standardized hardware wasn't used. Exactly what these plots mean, you know, is a little hard to infer too much from the plots. So then in the CNN category, this was using both MNIST and CFAR. Some participants did not finish CFAR, so they're kind of by default not going to be as far over. But again, within the timeout, nobody was able to check all the instances. And so there are a mix of both satisfiable and unsatisfiable examples for most of these. That kind of showed up earlier in the ACAS-XU hard table. And then there's some results submitted for a couple of the other CFAR networks. And most participants didn't get to these yet, though. So again, we had prioritized MNIST over CFAR just in the interest of time. But I think as we'll get to the discussion, others are going to look at these. Then in the nonlinear category, we only had 3 participants in the end, and several of these instances as well, people had timed out before solving all of the problems. Right, so I think we learned a lot of important things by going through this effort. So one was, you know, in mandating ONNX, we ran into a variety of issues with this. So for example, the precision used to represent floating point numbers within the networks themselves, there are variations among this within different learning frameworks and within ONNX. Some translators may add superfluous layers, so unnecessary and flattens and things like this. And then some translators would perform a conversion of fully connected layers to convolutional layers. So some sort of manual conversion, or our own implementations of translators sometimes were necessary. Another thing to point out with Onyx, while it's an interchange format and what we would encourage people to be using still, another thing to be aware of, there are some different versions of it. So it's not just Onyx, it's Onyx plus what version of Onyx you're looking at. There are some version compatibilities that would need to be looked at in more depth as we try to standardize things on a format. Another thing that came up, some methods need to transform the networks. One set of participants in particular, they needed to add a representation of a gradient into the network itself. And there were some compatibility issues between the learning framework they had used and Onyx. I think most, if not all, of the benchmarks required some form of normalization. So a simple one is within MNIST, just converting an integer color representation to floating point. So how do we formulate these aspects of the benchmarks beyond a README and extra documentation? This is, of course, a normal problem that shows up in a lot of just normal neural net usage, not trying to do verification, but it is important as we try to have some formal results on these. The size of the input sets are very important, so that epsilon in the local robustness, or the initial constraints used in the properties for ACAS-XU. So roughly, if that's larger, things are going to be harder, but that's not always the case. We did also identify some mismatches in the tool results, some of which would imply some soundness bugs in the implementations of the tools. So for example, some mismatching SAT and unsat cases. So those are things participants will need to look at in more depth. So I just compiled these and we'll kind of open things up for discussion. But some of my ideas and thoughts, as well as some of those I've compiled from the discussions with the participants. So a lot of machine learning competitions are run asynchronously. So perhaps instead of having a deadline, like what we tried to do this year, although it was fairly rolling, allow submission on an asynchronous basis. So if you want to compete in this, rather than having it necessarily tied to a conference and a presentation at a conference, just sort of allow people to submit results. We'd want to talk about how to do that for trying to standardize hardware on which things would run, since what we're looking at here is performance and not accuracy, right? So what we would test this on becomes important. We may modify the category organization. I'm not sure, based on the benchmarks that we ended up having, whether the current organization makes sense. So maybe having an organization into problem-based instead of architecture-based. So most of the examples, other than the ACAS-XU ones, were adversarial robustness for image classification. As other problems start to have results, and there are other problems that are, and other machine learning models that have verification results for them, we may want to have it be sort of problem-based. So image classification, this kind of input-output invariance that ACAS-XU has. So we're trying to use this as an opportunity to provide feedback for the VNN lib standard, an attempt to use the standardized representation of specifications in the future. So two examples of that. The first is that within the draft VNN lib standard, there's a subset of operators within Onyx allowed. So we may try to modify or transform the benchmarks that we have to match those. So for example, within Onyx, there's multiple ways to do matrix multiplication and similar things. So trying to just use one standard general operator for that is one thing that the VNN lib standard is trying to do. The other would be to specify the properties within the specification language they've defined, which is SMT lib based. Right, and I'm I think, almost finished. So other things, so we need to standardize the execution machine so that we have, apples to apples comparisons, because right now the charts that we presented, it's sort of difficult to interpret because everyone used different hardware, right? So what's 5 minutes on a cloud computing server is different than what 5 minutes is on a desktop or a laptop or whatever. So you need to try to have a mechanism for that. Related to that, maybe automating submission and execution processes and repeatability. So we haven't done repeatability yet. Again, the participants submitted results. Then other generalizations of having more benchmarks. There were some interesting CAV talks earlier today related to that. Other layers or activation types. A couple of things to point out in these benchmarks. I don't believe any of them use batch normalization, max pooling, or some of the other layers that commonly show up in real models, particularly in CNNs. We tried to solicit papers this year for the VNN workshop for benchmarks, but we didn't get a whole lot of interest in that, but hopefully we'll have, we could potentially use this workshop in a similar way to how Arch is used to collect benchmark papers. And then, of course, having sponsorship and prizes in the future would be something we want to do. Okay, so thanks again to all the participants. And I'm sorry if I missed everyone, but I kind of took the people who were most active in the GitHub and acknowledge our support that helped make this effort possible, especially that of the Assured Autonomy program. And then we can sort of open up Q&A now and discussion, other suggestions. And this QR code again goes to this draft overleaf report. All right.
Yeah, there's a few questions. One question in the chat, also one question in the YouTube channel. They're kind of related. So I will just read the question from YouTube. Yeah, thanks for running the competition. Have you observed that solvers give different results on the same benchmark, for example, SAT and SAT?
Yes, so that did come up in a couple instances, so not many, but that does imply a soundness bug for some of the tools. So we did observe that at least in a couple instances, and that's part of the reason to do this as well. This is sort of a manual fuzzing effort, if you will, but trying to try different examples and benchmarks and things, you may run into things you haven't seen before. So we did find that, so we need to look into those in more depth and fix whatever those soundness bugs are.
And there's a suggestion from Stanley that we can ask participants to add a second column to their results with SAT and SAT unknown to check for consistency.
Yeah, so I mean, I can tell you some of my thoughts about how we would improve the result submissions. So I think we need to specify a standard, probably CSV format that people would submit. Then we can generate this, these individual column tables. If you go look at the report, the way things are organized, there's a column sort of for each tool. And right now, there's some manual intervention to have identified these SAT and unsat instances. Yeah, so that would make things, that would improve things a lot and avoid manual checking.
Yeah. Cool. Is there any other comments, questions from the audience? We're monitoring the chat, the YouTube channel, as well as the Slack channel.
Or you can raise your hand.
Yes.
Within the Zoom.
Yeah, there's Rebecca. I unmuted you.
Hello. So I had a question from Stanley. For Stanley. So sorry, maybe I didn't understand this quite well. But if you compute all the way to the leaf, first off, some leaves are not achieved because there's a bug in the program. And then once you achieve the leaves, sometimes the leaves need to be further dig down in order to achieve the counterexample problem. How is it that you backtrack going backwards to the root of the problem, to the root of the program?
Sure. So I think this is specific to the method that I had presented, but the sort of short answer is that if it's not achievable, we don't split on those neurons. So we only consider splits if it's achievable. If it's not achievable, we skip that neuron, go to the next one.
Okay, so once it's not achievable, you wouldn't consider it as like an abstract or concrete. You just go for the second one to just basically verify what is verifiable. Then after that, you would go and dig deeper down to. Okay, got it. Thank you.
Okay, so just an aside, and we're almost out of time. I went ahead and I launched a poll about our format that we tried with this flipped classroom format. So we hadn't done this way before, and since that was the original guidance we got, we thought we would try it. So we're curious how it went, or your interpretation. So if you don't mind clicking on that. Voting on one of those options in the Zoom poll, we would appreciate it for planning future events. So I see a question related to the competition in the Zoom chat. Yeah, so we can talk about how to arrange that. I mean, the answer would be yes. I think anyone who's interested in being involved, everyone is certainly welcome to participate and do things like that. So I would say for this iteration on the rolling basis of submission, we'll just continue the discussions within the GitHub on the GitHub issues. And I think that's the reasonable mechanism. So in the longer term, there's probably a little bit of internal discussion that needs to happen. But for right now, I'd say everything on the GitHub issues is sort of reasonable. Yeah, so there's a question in the chat about kind of related to sponsorship, such as perhaps by Amazon with EC2 or other vendors who do machine learning and cloud computing things, or possibly using the CPS-VO, which is a virtual organization sponsored by the NSF. So, we're certainly open to doing sponsorship. I think it's sort of just a matter of getting people involved in that. Yeah. So I think that, go ahead.
I think my question is more like, if we do some apples to apples comparison, assuming there's going to be a central place to run measurements. Some of these things take a long time, like the oval benchmarks, 1 hour timeout, 300 benchmarks. And then if you have N tools, it's going to take like days or weeks to run if you have a single machine. So you really need a large number of machines that you can access. So having sponsorship just for like cloud computing time would be helpful.
Yep, I agree. It's something we should look into. And being affiliated with CAV, we tried to advertise a little bit regarding sponsorships. So it's something we definitely need to explore in the future. Yeah, because there are programs that exist, particularly I know of through Amazon to get access to do that type of thing. Okay. Any other comments, discussion? So I'm going to close the poll, I guess. We had some response. So can you see the polling results?
Yeah, we received 11 response. 6 says well, 5 says okay.
Right. Well, you know, depending on how long our virtual formats for things continue, it's something to consider for future events. Obviously, having a little bit more lead time in advance for participants to watch videos and things, I'm sure would be good. And you know, those kind of mechanisms. But if you have suggestions, feel free to let us know. Anything else from your end, Qinglu?
No.
Okay, all right. Well, I'd like to thank Qinglu for helping organize, and thank all of the authors and keynote presenters and speakers and everyone who asked questions and participated, and all of you in the audience who watched. I hope that you enjoyed the workshop, and we look forward to you know, future workshops like this, continuing VNN just feel free to get in touch about any of those things.
Thank you, Taylor. Thank you, everyone participated in this workshop.
All right. Thanks, everyone. Have a good afternoon or evening or middle of the night. And yeah, thanks especially to those, I know we had some participants, at least in Europe, so thanks for staying up. And if we had any in Asia, really thanks if it was the middle of the night or so. So thank you. All right. Thanks, everyone. Goodbye.
Bye, thanks.